Recording to the computer. Okay, I believe it's recording. Okay, I'm going to share my screen real quick. So you can see my screen right now, right? See, you see the
Yeah,
PowerPoint.
yeah, I see
Okay.
the PowerPoint.
So this lesson is going to be on map projections and the pros and cons of the 8 most common map projections. Contrary to what people say, the Earth is actually a sphere, which is a difficult shape to convey on a two-dimensional surface. Below are 10 actually of the most common map projections. Before we get into it, can you think of any like potential issues that you could run into trying to map a round thing such as the Earth on a two-dimensional surface?
I mean, yeah, I can imagine a few things, but I can't think of like the right way to say it. I know what you're talking about though. Like I see issues with it. I
Okay,
see
yeah,
how it would be a problem for a lot of people.
yeah. Well, the first what we're going to get into, the way I'm going to explain this is the orange activity. Obviously, this is over Zoom, so it doesn't work as well. But if we were in person, you distribute an orange like this to orange like that to all the kids in the class, and a Sharpie like this. And then you would take your best and do your best to take your Sharpie and do your best to draw a rough representation of the globe onto your orange. I did a little brief one while I was waiting for you to like come into the meeting. That's like North America and South America, South Pole, or
Mm.
Antarctica, North Pole, etc. It's not a great
Yep.
drawing, but you get the gist of it. So
Mhm.
once that were to happen, you then peel the orange off. I'm not going to peel it because I would be just sit here peeling for you. That'd be a waste of time. But as you can imagine, it's quite difficult to peel, to try to get one continuous peel off this orange, similar to how it would be if you were trying to accurately map the world. It wouldn't be like a perfect shape, and it would not be what you perceive to be a map, as you know, as you've learned throughout school. Um, it's obviously very difficult to accurately convey the world on an orange, but the odd shape of the peel should give you some indication of the difficulty cartographers have run into when trying to represent the Earth on a map. That's another example right there. Obviously, that is way better than anything I or you or anyone who doesn't have an excessive amount of time on their hands could do. But kind of getting the gist of like the difficulty of representing the Earth on a two-dimensional object. So now to go into some of the like very common projections and the pros and cons of those. First up, we have the Mercator. This projection was developed by uh, Gerardus Mercator back in 1569 for navigational purposes. Its ability to represent lines of constant course from coast to coast made it the perfect map for sailing the seas. Its popularity was so great that it became used as a geographic teaching aid, even though the projection grossly distorts country sizes. Like if you compare Africa and Greenland, for example, appear to be like the same size here, right?
Right.
Well, in fact, Greenland could fit into Africa. In reality, Greenland should be able to fit into Africa 14 times. Like it isn't like there's a gross distortion, and you can kind of tell by the gap between the lines of, I want to say latitude. I could be wrong though, but it's one of the two, the horizontal one. Can you, off the top of your head, can you think of any more of like pros or cons that could come with this map, or no? You can say no. You can
I
say
mean,
no.
I think you listed the biggest con, which is like it's like kind of misinformative for like Greenland and Africa.
Yeah,
I don't know. I can't really think of
yeah,
any
that, yeah.
cons, which is why I'm in this class. I'm here to learn. So.
Okay. Next we have the Robinson map. This map is known as a compromise. It shows neither the shape or landmass of countries correctly, actually. Arthur Robinson developed it in 1963 using a more visual trial and error development. Uh, a quote from him was actually, I visualized the best looking shapes and sizes. I worked with the variables, and until it got to the point where if I changed one of them, it didn't get any better. It was only at this point that he worked out the mathematical formula that represents the Robinson map. The curved meridians give it a nice spherical look as well. The con of this, obviously, as I said, neither shape or landmass is accurately represented here. And it doesn't really, given the curved like lines of the curved meridians, it doesn't really provide that much of a like navigational or like purpose either. So aside from this one being on like the walls of school to give kids just a general idea, this one is not very effective either.
I was gonna say, is this like the most common one used in school? Because I feel like if you look up picture or like of a map of the world, I see this.
It's one of there's a couple, like it's not exactly like a verifiable thing, but like
Mm-hmm.
there's like two or three that are way more common. Like the next one up is you'll see is not at all common. It's known as the Dymaxion. Uh, this projection was released by R. Buckminster Fuller in 1954 after he worked on it for like decades. The world in this for this map, it's projected onto the surface of an icosahedron, which is like this weird, almost gem looking shape to my knowledge, which allows it to be unfolded and like flattened down. The purpose of this was he wanted to like look at Earth within like the terms of Pangea, because in reality the globe doesn't necessarily, or a map doesn't always represent it, but the land masses within like the world are actually relatively close together and connected in the grand scheme of things, but we never look at it from above. And the objective of this map, like the desire was to present a projection that had like no right way up and lose the north south and like cardinal directions. um it does accurately represent all the land masses or whatever, but obviously because of his goal of removing the cardinal directions and aiming for one big island, this map doesn't really serve any functional purpose. As like if you didn't know any better on a glance, you probably would not even assume that that is Earth. Looks
No,
very weird. It serves no navigational purpose either, but it effectively conveys what the Earth would look like on a flat surface if it was folded and whatnot and manipulated to be effective. Next up is the Gall-Peters map. This is part of like a subsect of maps that are called cylindrical maps or cylindrical projections. And this is a cylindrical world map projection that gains accuracy in surface area. It's named after James Gall and Arno Peters. Gall first described it in like 1855, but then Peters was the one who actually like put it into practice in 1973. And this one stands out a little because the guy Arno Peters, he was marketing it. So like he was like pushing it and like trying to sell this as a map in the 70s. Obviously, we saw it looks very similar to the first map we saw,
Mm-hmm.
which the Mercator map, but the difference between the Mercator map and this one is this one also skews and like warps projections, but it does so more for to like towards the equator and whatnot. And he was marketing it, calling it a new invention that allowed poorer and less powerful nations to be restored to their rightful proportions. And he like put it in a pamphlet and like was trying very hard using it as like a monetary tool. Obviously, this also has a lot of warping as well. It does it the opposite way. It makes the equator size quite big, and it makes the like towards the poles much smaller. While it is slightly more accurate, it's still not exactly fully representative of what a map should be. Next up, we have the Sinu Molewide. This was developed in 1953 by Alan K. Philbrick. It fuses the sinusoidal projection with, which was first used in like the 16th century, with Carl Brandon Mulwade's map of 1805, and challenges our assumptions of how the flattened globe should look. It's an equal area projection that maintains like relatively accurate landmass, but when you look at it, like the cracks and the like almost looking like shattered cracks at the bottom and the split at the top make it a little difficult to fully comprehend distances and whatnot. And it's hard to imagine this in a spherical sense. You kind of can, but it involves like piecing it together like a puzzle, and it warps the lines of longitude and latitude dramatically. Next, we have the Goods Homosaline map. This was developed by John Paul Good in 1925. This projection regains accurate country sizes by adding these like interruptions. I think of it as more of a smoother version of the Sinu Molewide,
Mm-hmm.
because it's like a little more. If you were good at peeling your orange, which I personally am not, and for this activity, this is most likely what it would look like. if you were to actually peel the Earth and lay it flat, this is probably the most accurate representation of that. But obviously, it splits Antarctica into 4 different things. It splits Greenland down the middle, and the oceans are hard, difficult to read. This next one is known as the orthograph. It was inspired by the Demaxian map. Narukawa. This is his map, which was made by dividing the spherical surface of the map into 96 triangles and then like piecing those triangles together into a tetrahedron that can then be unfolded, which is a little complicated, but that's not something you really need to know to understand the concept. But what this map allows is you retain the correct proportional sizes of the continents, and the layout is relatively recognizable. The only issue is obviously it has 0 navigational purposes, as you can tell by like the middle center. Like if you're trying to use this map to travel,
Right.
you're kind of in trouble there because it's not how the Earth works. This next one is within the subgenre of cylindrical equal area or cylindrical projections, but this one is a little different because it also functions as an equal area projection. This map is known as a cylindrical projection because of its straight lines of longitude and latitude, and its shape is sacrificed in order to represent countries in their correct proportional size. This is done by narrowing the lines of latitude as they approach the poles, as you can see right there. And in order to compensate for the missing convergence of the lines of latitude, it's a really interesting and alternative like view of the planet. It's obviously got its problems, like it's making things a little wider than they should. Like Alaska, I don't believe extends that far. Antarctica looks like a ridiculous landmass right there, when in reality it's not quite that. It's also very similar to the ones we've seen before, but I believe the difference in this one pertains to how the poles are represented in terms of width. Our second to last map, we have the Pierce-Quinoncio map, which is kind of like a bird's eye view type of thing. Obviously, it's not used very much in geographic purposes like other ones. This projection is presented with the North Pole at the center and the 4 quadrants around this, giving you a projection that can be tiled perfectly. Believe it or not, this actually isn't that bad for navigational purposes because
Really?
I don't really understand it. It's a bit above my pay grade, but supposedly it's consistent and linear throughout. Like I read up on it and it can be used but not by obviously an inexperienced sailor, but supposedly you can like tell the time based on like where you are. I don't really know. It was a lot of like pirate and like navigation jargon that was above my understanding, and that's not necessarily needed for this class, but yeah. And then this final one is known as the Winkle tripole. This is a modified Amazuthial projection. It was created by Oswald Winkle in 1921 and was developed with the goal of minimizing the 3 kinds of distortion, which are area, direction, distance, as we've seen throughout several of these. This is somewhat similar to the Robinson map we saw before, but this is allows all the parallels to be curved, where that wasn't really before. The horizontal ones were still straight. These ones are curved on this as well, which gives this a spherical feel and feels the most similar to what, when we look at a globe or look at the Earth, this feels the most similar. And it doesn't have strong like warping distortion in any of the 3 categories as it mentioned, but it also doesn't perfectly represent any of those. So kind of falls short in that method a little bit. Now for exit discussion, as we've seen with these projections in the orange exercise, there's no perfect way to represent the Earth on a 2-dimensional surface, but there are better ways for certain purposes. Which of these maps, I can click back through if you need, but which one, based off what we learned today, do you think is the most effective?
I would say the most effective one.
I'll click
is-
back through for you.
Yeah, go back. I forget, the names are hard. That one's good. I do like that one. The Winkle. I like that one.
I personally think the Demaxian is really cool, but it obviously is not very
Maybe Robinson.
effective. The Robinson one, yeah. I
like
said the
that.
Robinson is very similar to the last one, the Winkle tripole, except that this one is curved horizontal. I don't remember if that's
I think the
longitudinal.
worst, the Axion or whatever. it was
Yes.
cold.
Yeah,
That one,
but that is one of the few that maintains an accurate land size and whatnot. But that
yeah, but
right there proves my
a
exact
map.
point. There is no. I'm sorry.
Who's gonna use a map just for accurate land size?
I mean, there's all sorts of purposes for maps. Like it doesn't always have to be the sea. You could be using it to explore the like land. Usually you wouldn't use a world map, but I'm
Or-
not an explorer. But that right there is a perfect example of what the point of this lesson. There is no one way that's like clear cut above the rest. Some at the end of the day, it kind of comes down to preference. Now, sometimes these projections can have effects on things outside the world of cartography. Can you think of any potential examples of that?
I'm gonna read that one more time. Sometimes these projections. No, can you give me some examples?
So throughout history, obviously, there's been as the very first one we saw how it had the how Greenland was manipulated and like or not manipulated but warped and looked very big, whereas Africa was a little smaller.
Mhm.
Uh, while most of the time these effects are unintentional and just coincidence, there is some truth in them that like textbooks in like North America and sometimes Europe will you deliberately like use a certain type of projection in order to warp other continents and make themselves seem bigger. Like I know China has like China, their textbooks, Asia looks a lot bigger. Like it's a very common thing actually. At least I don't know that personally. I've never seen a Chinese textbook, but during my research for this, I came across that. And Africa, the maps that that I saw growing up all throughout school and that you see in school are usually not very representative of Latin America and Africa's true sizes. And as I said, most of the time that's coincidence, but sometimes there are like geopolitical motivations behind that to minimize like what we perceive to be third world countries or less developed countries and make the United States or Canada or Europe seem bigger. And obviously, bigger your land is, the more confidence your people could get from that. It's obviously very minor, but it's interesting to think about nonetheless. Now, another thing, if we were in person, I would now have you complete your exit slip with one question regarding the different types of projections. Could be like anything.
Okay.
Since you're not in person to write that down, do you have any question at all? Doesn't have to be high level. Like it doesn't have to be like a level 4 question or anything like that. Just
No, yeah, I know.
left up.
Um, why is it all the maps we looked at today? Those were all like a long time ago. Why isn't there a new map that's like very like completely accurate? You know, like a 2010 or above map that's been created to like fix all the errors of the other maps.
Well, that's like the whole like problem that they've always been wrangling with. The reason I would say for that is I don't think anyone knows another way. I obviously it's not my career, but I can't think of one. And
Really?
because like that's what the orange represents. Like
Right.
this perfectly smooth thing, like cannot be truly conveyed on a 2D surface. So every map is going to have its problem, essentially. I
Well, I
don't,
guess the benefit of a phone, get like a 3D and you can like swipe through it.
yeah, obviously maps are becoming less and less prevalent, but that would be it today. Thank you for paying attention.
No
I'm going
problem.
to
Pleasure.
stop sharing my screen now and